This is a lesson on the buoyant force, also known as Archimedes Principle in fluid statics. The buoyant force is an upward force from a fluid on a submerged object. So whenever you put something in a fluid, that object will experience a buoyant force. The buoyant force can be calculated in this way. The buoyant force equals the weight of the fluid displaced by the submerged object. And I found this to be a tricky concept for a lot of students as we move into this material. So take some time to think about, what is the fluid displaced by a submerged object? Here's the equation. The buoyant force is the weight of the displaced fluid. And remember, weight is mass times gravity. And if I want to find mass, I can just use density and volume in order to find the mass. When I think about submerged objects, let's put some water here. Here's some water. A rock may go all the way down to the bottom so that the volume of the displaced fluid will equal the volume of the rock. However, I might put a stick or a log into the water and that won't sink. So the volume of the log here will be greater than the volume of the displaced fluid. These two things will not always be equal, and sometimes you will have to calculate the volume of the displaced fluid or the volume of the submerged object. Let's look at the buoyant force a little bit closer. And why do heavy things float? If there's a density difference and one density is larger than the other, it seems like that object should just float. But of course, that's not the case. Ships float, right? So how do we get heavy things to float? The trick here is to take that object and shape it so that it displaces fluid, that it displaces enough fluid that it gets a large enough buoyant force, right? So what we want to do is get fluid out of the way. That's why we have to look at the displaced fluid. So let's look at the problem I picked out here to kind of think about what's going on here. It says, what volume of water must be displaced in order for a 125 centimeter cube chunk of clay to float? So it's just a chunk of clay, and it's about like this, 5 centimeters by 5 centimeters by 5 centimeters, right? That's 5 cubed. So you just have like a chunk of clay, and you can take it and you can mold it into a shape, right? So that shape of the clay can displace fluid. If the clay was all in one chunk, it would sink. But if you shape it in the right way and displace fluid, it will float. So let's kind of draw here. Let me draw a cup here. I'm going to take the clay and kind of make a cup out of it. And so it's circular. Maybe you can think of it maybe like a bowl just sitting in the water. And so it's displaced some water out of the way. And when I think about that clay being in the water, I'm thinking about the free body diagram. There's a weight of the clay. And because it's in water, it will experience a buoyant force upward. The second law of motion tells us that the net force has to equal mass times acceleration. We're in fluid statics, so we know the acceleration is 0. There's a buoyant force upward and the weight of the clay downward. And I can assign a coordinate system so that we can have our plus and minus signs. I'll just say plus y is upward. Okay, so we see that the buoyant force, in order to cause the clay to float there, has to equal the weight of the clay. So the buoyant force equals the weight of the clay. Well, I can take what I know about the buoyant force. The equation on the previous slide that I showed you, the buoyant force is going to be the density of the displaced fluid, which is the water in this case, right? The volume of the water, so that gives us the mass of the water, times g. That's the weight of the displaced fluid. And what we're going to do is we're going to set the weight of the displaced fluid, the buoyant force, equal to the weight of the clay. So weight of the water times the volume of the water times g, that's the weight of the displaced fluid, and will equal the weight of the clay. Well, the weight of the clay is rho clay volume clay times g. Because we're dealing with weights, g is on both sides. I'm going to cancel that out. I'm going to do a little bit of algebra on this equation. And we're solving for what volume of water, so let's isolate that on one side. The volume of water equals rho of the clay over rho of water times the volume of the clay. They tell us assume clay has a density of 1.7 grams per centimeter cubed, so I can put that in there. I'm going to remind us that the density for water is 1 gram per centimeter cubed. If you have fresh water, 1 gram per centimeter cubed. So that's the densities, the ratio of the densities, and then the volume of the clay is 125 centimeter cubed. So when I solve this, the volume of the water is going to be 212.5 centimeters cubed. You can do some conversion on this. I was thinking about it, if I have a cube that big of clay, how much water would it have to displace in order? So that's how much water. To put it more in everyday terms, because I'm an American, that's 7.2 fluid ounces. So a little less than a cup that you would have to displace. You'd, shape out that play. So when you're working with buoyant force, you're going to go back and do a force analysis. Remember to draw free body diagrams that may be relevant, and I will be grading for them on homeworks and exam. You will apply Newton's second law. Often it will be in 1D. The net force is ma. If you're in static situation, the acceleration equals 0, and things will work out easier. Identify knowns and unknowns and solve. Make sure you reflect on your answer and your problem-solving strategy. So I picked out another problem here, a paperweight. It says a paperweight, when weighed in air, has a weight of 6.9 newtons. When completely immersed in water, however, it has a weight of 4.3 newtons. Okay, so this is weird because the weight of an object does not change. Right? The weight due to gravity is the mass times the gravity. So the mass doesn't change and gravity doesn't change when you stick something in water. So there's some weight that this paperweight is. This second force here, and maybe I can think of it like if I put the paperweight on a scale in air and on a scale in water. The reading on those scales are going to be different. This is similar to if you stand on a scale in an elevator. If you stand on a scale in an elevator moving upward, you get a larger value than what you actually weigh. It's an apparent weight, right? And what the scale is actually telling you is the normal force that's being applied in order to cause that motion. So when I look in this situation, there's an initial normal force, N1, 6.9 newtons. And then there's a second normal force, 4.3 newtons. They're two different situations. So let's draw these situations, and my suggestion is to draw a free body diagram, right? So in air, let's draw a paperweight. That's just a paperweight. In air, the paperweight has a gravitational force on it, the weight due to gravity, okay, mg. You can call this W, you could call this Fg. I don't care as long as you define it as the weight of the object. In air, there's also one other force, the normal force upward, N1. And in this situation, we know that the net force has to equal ma. There's no acceleration. There's a normal force upward, and I'm going to call upward the positive direction. So I have the normal force upward minus the gravitational force down, and that has to equal 0. And that just tells us the normal force equals the gravitational force, and that equals 6.9 newtons. Okay, so that's how much the paperweight actually weighs. That's the weight of it. That's the normal force in the first situation. In the second situation, let's draw the free body diagram. So if we're going to put the paperweight in water, okay, if I put the paperweight in water, it still has a gravitational force on it. It does not change. This is the same gravitational force. And so that's 6.9 newtons. Okay. It says that it's underwater. So, of course, there's a buoyant force on it. There's the buoyant force. And then also there's this other weight, this apparent weight, the normal force that whatever surface has to hold in order to make sure that the object does not float up or sink further down. All right, so like it's on the bottom of whatever, you know, container it's in, and it has a normal force in that situation. So when I do F net equals ma in this situation, again, we have no acceleration. I have the normal force 2 upward plus the buoyant force upward minus the force of gravity downward. Okay. And what they're asking here is find the volume of the paperweight. The volume of the paperweight is going to be buried in this buoyant force. What I'm going to note is that the buoyant force is the weight of the displaced water, right? This is the weight of the displaced water, displaced fluid. The weight of the displaced fluid is rho of the fluid times the volume of the fluid times gravity. And I'm going to note in this situation, when the paperweight is under the water, the volume of the displaced fluid equals the volume of the paperweight. So I can put in here the volume of the paperweight. Okay, so I have an equation set up. I'm going to solve for the buoyant force. That will equal the gravitational force minus N2. The buoyant force, I'm going to put in my expression for buoyant force over on this side. Rho of the water, volume of the paperweight times G. That has to equal the force of the weight of the paperweight minus the normal force in the second situation. I'm going to keep solving and isolate the volume of the paperweight, rho water times G, and I'm going to plug numbers in. The force of gravity is the initial normal force. The second normal force is 4.3. I'm going to divide by the density of water, which is 1,000 kilograms per meter cubed, and the gravity. The volume of the paperweight turns out to be, when you run this through your calculator, 2.6531 times 10 to the negative 4th meters cubed. Okay, I didn't expect a big number. It's a paperweight, right? So it's not a big number. And when I look at this, I converted it to centimeters cubed just to get a little bit better grasp of this number. Is it making sense? Does my answer make sense? So 265 centimeters cubed. Well, my clay before was 125 centimeters cubed, and that was like this big. So that's like a paperweight, I guess. If it's a circle, if I set it equal to 4 pi r cubed and solve for the radius of a sphere, I get the radius to be 3.986 centimeters if I have a paperweight that's a sphere, okay, with that volume. So it's about this big. The next problem I picked out deals with a partially submerged object, which is a swimmer. A swimmer floats in the ocean with 90% of his body below the surface. The density of ocean water is 1,025 kilograms per meter cubed. What is the swimmer's average density? Okay, so if I think about a swimmer just floating in the ocean here, I know that there's going to be a gravitational force on the swimmer, his weight, and then also there's going to be a buoyant force. When I apply Newton's second law here, I see that the buoyant force basically has to equal the gravitational force in order for the swimmer to just float. F net equals ma. The acceleration is 0. The buoyant force upward minus the gravitational force downward has to equal 0. So I get the buoyant force equals the gravitational force. Okay, well, I know what the buoyant force is. The buoyant force is the volume of the displaced fluid, which is in this case ocean water. So the volume, the weight of the displaced ocean water has to equal the weight of this swimmer. I'm going to write in what I know about weight. I'm going to take the density of the ocean water, the volume of the ocean water, and times G. That's equal to weight. The weight of the swimmer is going to be the density of the swimmer, which what we're trying to find, the volume of the swimmer times g. Okay, so gravity cancels on both sides, and then I also need to incorporate the relationship between the volumes. It says a swimmer floats in the ocean with 90% of his body below the surface. So that's how much fluid has been displaced. The volume of the ocean water displaced here, the displaced fluid, will equal 0.9 the volume of the swimmer. Okay, so we can put that down here. This is the volume of the ocean water. So rho of the ocean water times 0.9, the volume of the swimmer, has to equal the density of the swimmer times the volume of the swimmer. And you can see the advantage here. By plugging in this relationship, I get the volume of the swimmer, canceling on both sides. And I can solve for rho of the swimmer. That's why I'm solving for. Rho of the swimmer equals 0.9 rho of the ocean water. I can plug values in here now, 0.9 times 10^25, and rho of the swimmer turns out to be 922.5 kilograms per meter cubed. And I expect that to be less than the 1025 because he's floating. The density of the swimmer should be less than the density of the fluid. And I wanted to point out here, if you remember about specific gravity is the density of the object in the fluid divided by the density of the actual fluid. So in this case, we see that I have 922.5 over 1025. That equals 0.9. And so this is the advantage of using specific gravity, is that this here is the fraction submerged. So if you have a really light object that isn't very dense, for instance, air, you can see that the fraction submerged is not going to be very much because you don't need to have a large force in order to support air. It doesn't weigh a lot. The last problem I chose for us to work on is the hot air balloon. A hot air balloon hovers at low altitude, so if it's hovering, the acceleration equals 0. It's hovering at low altitude on a calm, clear day. The total weight of the balloon, including its load and the hot air in it, is 20,000 newtons. Two parts here. What is the weight of the displaced air, and what is the volume of the displaced air? Okay. So when I look at the balloon, and I drew a balloon here for us, just a rough sketch here, hot air and the balloon here. It tells us that the weight of the balloon and everything, so this gravitational force is 20,000 newtons. So I'm going to put that down here. The 20,000 newtons is the weight of the balloon and everything there. We know it's floating in the air, so there must be a buoyant force upwards. I can assign a coordinate system because I'm dealing with forces. I'll put plus y upward. And I know that F net has to equal ma. In this situation, we know that it's not acceleration. It's not accelerating. There's a buoyant force upward minus the gravitational force downward. And this equation gives us that the buoyant force has to equal the gravitational force on the balloon, which we know is the weight of the balloon and all its contents. So that looks like the answer for A. The buoyant force is the weight of the balloon, so I'm going to say that the buoyant force equals 20,000 newtons. Okay, so there was part A. I'm going to do part B over here. Part B asks the volume of the displaced air. Okay, so when I look at this balloon has displaced air outside of the balloon. There's hot air inside, but we want to know how much air was displaced outside. Well, we know the buoyant force has to equal the weight of the displaced air. So I'm going to put weight of the displaced air. The buoyant force I know is this 20,000 newtons. The weight of the displaced air is going to be rho of air, the volume of the displaced air, which is what we're looking for, times gravity. Okay, so I'm going to solve for the volume of the displaced air. That's what we're looking for. The volume of the displaced air will equal the buoyant force, F buoyant, divided by the density of air times gravity. Okay, so all of these are numbers I know. The buoyant force we know is 20,000 newtons. We can look up the density of air in any book. It's 1.29 times 10 to the negative third. And then I'm going to multiply by this factor of g down in the denominator. When I run this through the calculator, the volume of the displaced air turns out to be 1.582, and I'm expecting this to be a large number, times 10 to the 6th meters cubed. That's pretty big. 1.6 million meters cubed. Okay. I thought about that, like how big is that? That's not a comprehensible number for me. I thought, well, maybe if I let the balloon be approximately a sphere, I could solve for a radius for how big that balloon had to be in order to hold up 20,000 newtons. And I get the radius here. If I solve, the radius is 72.3 Newton meters, which seems really large to me. Maybe this is not a realistic result. That's a really large balloon in that case. And that concludes the lesson.